Hello everyone, this is Oshani from Cheenta.com. So yesterday I was working with our Math Olympiad junior group and we were talking about Fibonacci numbers and a little bit of algebra. So it was so beautiful, I thought that I will share this with all of you, everyone in the community. So here is the plan. We will talk about Fibonacci numbers, we will talk about golden ratio, and we will then use a little bit of code to find out a ton of Fibonacci numbers. And while we're using that code, we will talk about the philosophy of algebra. What are variables, what they really are, okay? So the entire exercise is an interdisciplinary exercise. So you learn algebra, you learn coding, you learn sequence of numbers, everything is coming together, and that's what makes it so beautiful. So let me first quickly tell you what Fibonacci numbers are. Maybe some of you are not aware of Fibonacci numbers. So it's a sequence of numbers. Sequence means there's a first number, second number, third number, fourth number, but there's a bunch of numbers. But you know, you have labeled them as first number, second number, third number, and so on. So in the Fibonacci sequence, the first number is 1. This is the first number. The second number is also 1. The third number onward, it is a trick to find them out. What you do is, you just add the two previous numbers. So for example, the third number is just the sum of the last first and the second number, which is 2. The fourth number is the sum of the second and the third number, which is 3. Then it's 5. Then it's 8. You see, at every step, we just add the two previous numbers. So for example, 3 and 5 are added to give us 8, right? 2 and 3 are added to give us 5, and so on. So we have this sequence, which is the Fibonacci sequence. And fun fact, Fibonacci sequence was not discovered by Fibonacci. He just learned about it from Indians, apparently. Just like Pascal's triangle was not invented by Pascal. About 600 years before Pascal, there was an Indian mathematician called Olympiad who had developed something called the Meru Prasthar, which is absolutely the same thing as the Pascal's triangle. Of course, Pascal worked on the Pascal's triangle a lot more and invented the mathematical properties of it. So credit goes to Pascal as well. Coming back to Fibonacci sequence, we have this sequence of numbers. And there are beautiful properties of the sequence. The first few the one property that we would like to talk about is the golden ratio property. Golden ratio. So what is the golden ratio? Golden ratio is a magical number. Let's call this number a magic number. It's a magical number which has a very interesting property. If you subtract 1 from the number, or if you take the reciprocal of it, reciprocal means you flip the number. So for example, reciprocal of 2 by 3 is 3 by 2. Reciprocal of 5 is 1 by 5. So if you multiply a number and its reciprocal, you will always get 1. That's what reciprocal means. A number and its reciprocal multiplies to give you 1. So the magic number has this property that if you subtract 1 from it, or if you flip it, that is, if you take the reciprocal of it, you will get the same number. They will be equal. See, this is the interesting part. We don't know what the magic number is, but we have a property of it. So even without knowing what the magic number, we can write down a mathematical equation for it. So instead of writing the word magic number, we sometimes write for a shorthand x. So x minus 1 equals to 1 over x. So instead of just writing magic number, I wrote x. I could have written just a blank. So a blank minus 1 is equal to 1 divided by the blank. We don't know what number should go inside the blank. That we should figure out. Definitely it's not 5. So let me just give you an example. 5 is not a magic number. 5 is not a magic number. Why is that? Well, 5 minus 1 is 4. 1 over 5 is 0.2, and they are definitely not equal, right? So 5 is not the magic number. So what is the magic number? What is that number which works? Well, that number is actually called the golden ratio. And it will turn out that this is approximately 1.6. You can make it better, like that. You can go into several decimal places to make it better. You cannot write it exactly in this sort of terminating decimals, that you cannot do, but you can approximately write it. It's 1.6, and you can check. 1.6 minus 1 is approximately equal to 1 over 1.6. You can calculate it using a calculator if you want, or you can just do hand calculations. You can make it better actually. It is 1.61. Then you can do another decimal place. I think that's 8. So you can make it better, but it's approximately 1.6. And how is that related with that sequence, with the sequence of Fibonacci numbers? Well, here is the relation. You can do the ratios. So let me just do one thing. Let me copy the Fibonacci numbers. And let's find out the ratio of the next number divided by the previous one in this sequence. So we have 1 over 1, which is just 1, right? The ratio of these two. Then we have 2 over 1, which is 2. We have 3 over 2, which is 1.5. We have 5 over 3, which is 1.66. And you can actually keep on doing this. Then we have 8 over 5. And then the next one will be 13, right? Because 8 plus 5 is 13. 8 plus 5 is 13. So 13 over 8. And the next one will be 21 in the sequence. So 8 plus 13 is 21. So 21 over 13. And you can keep on calculating this ratios. And you will see that it's stabilizing. It's almost always around 1.6. All of these values will be close to 1.6. Much later in your academic career, maybe in high school, you will learn something called calculus, where we can say more precisely what's going on. It's a very interesting thing going on. You have infinitely many ratios. None of them are precisely the same, but they all accumulate. They all get close to a certain number. This very mysterious number we do not know. We are unable to write it, but the values of the sequence of ratios, they get closer and closer to each other, indicating that there is this mysterious number. The existence of the mysterious number is given by the fact that these ratios get closer and closer to each other. So I'm getting ahead of myself. Maybe in the calculus class we will talk about this, but this one is absolutely fascinating. If you calculate these ratios, you will see exactly what's going on. And that's what we will do precisely. We will run a little bit of computer code to, show you what's going on. So we will calculate some of the Fibonacci numbers. We will learn how the notion of variable is used there. It's very important that you sort of grasp it. And then we will calculate all the ratios up to, let's say, 100 terms, and we will see that they are all getting close to around 1.618. Okay, so let's try that in the next section. All right, so if you don't know coding, do not worry, because this is not really a coding exercise. We want to understand algebra a little bit better, and that's why we are working with this little code snippet. The objective of this code snippet is to print a bunch of Fibonacci numbers, maybe the first 100 Fibonacci numbers, and also see what happens to the ratios of Fibonacci numbers, like the next number by the previous number, that ratio. And while we do this, we will learn a little bit about the philosophy behind the idea of variable in algebra. Okay, so to get started, let's create a variable called a and put the number 1 inside that variable. So do not think about this equality sign as equating a and 1. That's not what's happening here. Imagine this letter A as a box in which you are putting the number 1. The box was an empty space, and now you are assigning the number 1 inside it. So that's the first Fibonacci number. The second Fibonacci number is B, so I'm creating another box, another little storage space in which I'll put the number 1 again. This notion of a box in which you are putting the number, this is essentially what a variable is. It's an empty blank in which you put numbers, and you can update those numbers. I'll show you in a moment how that happens. Okay, now I'll use I equal to 0. I'll tell you what I is. Do not worry too much about this. It's just an index number. So I'll take a bunch of numbers from 0 to 99, and I will start with 0. So I equal to 0, and then I'll go up to 99. Okay, so I'll tell the computer that for I in range, let's say 10. So basically this tells the computer to take the range of numbers from 0 to 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So first 10 non-negative integers. For I in this range, I'll ask the computer to do something. And what it is? Well, I'll create a new variable called C in which I'll put A plus B. Okay? So what is A? What is inside A? 1. What is inside B? 1. So now I'm putting 1 plus 1 inside C. So C is another variable. Okay? C is another variable. Now, look at this very carefully, what I'm going to do now. Inside A, I will put B. So, A was a box which had the number 1. B is a box which has the number 1. Inside the box A, I'm putting the number that is inside the box B. So in this case, I'm just replacing the 1 inside A by the 1 that was inside B. Nothing really very interesting happening here. It's super simple in some sense. I'm replacing up one by one, but in a moment you will see what happens. So then I'll put inside B, I'll put C. So now what happens is, earlier inside the box B, I had the number 1. Now inside the box B, I have the number that is inside C. But what is C? C is just 2, right? Inside C there was 2. So I am putting inside the box B, I'm putting the number 2. Okay, so now I'm updating B, right? Okay, but C is still 2. It's not updated. So I'll just print C. Print C means whatever the value in C is, that will be printed inside this portal. Okay, so let's see what happens. Well, if I run this, let's see what happens if I run this. Well, first I'll go through this one step by step. First it prints 2, of course. C is 2 because A is 1, B is 1, and C is A plus B, so that's 2. So it prints 2. Okay, so for that happens for I equals 0. I started at 0, right? I equals 0. Okay, now it updates the value of I. It becomes I plus 1. So it increases the value of I. Okay, so it was 0, now I is equal to 1. Okay, so for I equals to 1, it will again do C equals to A plus B. But you have to be very careful. In this particular case, C is the new value of A, which is 1, and the new value of B, which is 2. So C is 1 plus 2, that is 3. C is 3. Okay, that's great. Now we again put the value of B inside A. So what is inside B? Well, inside B we have 2, we put it inside A. And similarly inside B we put the value of C, which is 3. So we are updating the value of A and B in every step. So in the class we actually can draw the boxes and check what's happening at each step. So this is sometimes known as a loop. So the same operation will happen for 10 times from 0 to 9, so 10 times. So this is what's happening. So you see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 numbers are there. So you have 10 Fibonacci numbers. You can actually do it. Just change the range to 100. You can actually run this and you will get 100 Fibonacci numbers. So the first 100 Fibonacci numbers. Okay. Actually, if you consider 1 and 1, then you will consider the last number in this list will be the 102nd Fibonacci number. So just with a little bit of code, you can actually print all the Fibonacci numbers. The other part that I was talking about is that you can calculate C over B. So before you update the value of B, you can actually calculate the ratio, which is again a variable, is C over B. Okay, so you can also print the ratio. So be very careful here. What I just did is before I update what is inside B, I actually calculate C by B. Because once I update B by the value of C, C by B will be essentially C by C, which is 1, which is always 1. So before I update the value inside B, I have to do this division. I hope you are getting the main idea of a variable in algebra. It's a blank in which we can put values and those values can get updated. Okay, so let's see what we get. So if I refresh this, you will see. So let's do one thing. Let's not print C anymore. Let's just print the ratio. So the ratios are So it starts with 2, 1.5, and then it all of a sudden becomes 1.6, 1.6, 1.6, and it becomes 1.619, 1.617, 1.618, 1.617. So it keeps on oscillating a little bit around that, and then it sort of stabilizes around 1.618. So it obviously doesn't compute up to all the decimal values. It computes up to a certain decimal value. So after a certain amount of time, you'll see that this absolutely stabilized. So this is kind of misleading, because this number, it's not calculating the entire ratio. So it's not giving all the infinitely many decimal places. It's just giving finitely many of them. So you're only seeing the stable version of it, the number which is up to this decimal place, it's the same. After this, there might be something changing. Okay, so this is the golden ratio. This is the golden ratio. So if I go and sort of create another one, so you can probably see it here. So, So you can see this here. So ratio minus 1. So if I subtract 1 from the ratio means this is the number, the last number. And let's do one more. Let's do 1 over ratio. So you see what just happened, right? If I subtract 1 from this number, and if I take the reciprocal of it, I'm getting almost the same thing. There is some difference in the last few digits, and that's because, as I told you, it has not reached the exact number. There are many more decimal places, and there is some difference. So if you go, let's say 1,000 Fibonacci numbers, this will be more stable. It will be a better approximation of the golden ratio. So this number, 1.618033, this number is a very good approximation of the golden ratio. So I hope you learned something from here. I always prefer mixing ideas from different parts of knowledge. Mathematics, computer science, physics, all of them should come together, because it's really the same thing, right? It's really the same thing. If you are enjoying this kind of mathematical videos, please care to subscribe and share. And also you can join our Math Olympiad program. Check the link in the description for more detail. Take care and goodbye.